Hello, everybody. This is a presentation made by myself of CFD Fair Service, Ruggero Poletto, and by engineer Jordy di Pierno from FSE PROGETTI. We're going to talk about a paper factory fire safety engineering approach, which has been made last year. This approach has been made according to the Italian regulation DM 3 August 2015, which is the regulation which defines how you have to make a fire safety engineering analysis in Italy at least, and has been made using a BIM CFD FSE approach, so using several technology at the same time, among which it's worthwhile mentioning Revit for the BIM generation, PyroSim and Pathfinder used in order to set up the CFD analysis, and FDS, which is obviously the solver which is going to use. Given the CFD analysis required by this case to be performed, we also made an FDS scalability in two scenarios, which were particularly big in terms of computational resources required, using FDS version 6.7.9 and CloudGIS PC hardware resources. I leave now I'll let speak Jordy in order to introduce you the fire safety engineering, and I'll speak later about the scalability part.
Hi. The Italian regulation DM 3 August 2015 defines 10 different strategies a fire engineer needs to assess in order to complete a fire design of a structure. For each of these strategies, the designer can apply the FSE, fire safety engineering approach, where the standard approach is not possible. In the design of a fire safety system of a paper factory placed in Lucca, Italy, the standard approach was not possible in the following strategies. S2, fire resistance. The fire engineers needs to guarantee the fire resistance of the structures of the building for the time required by the occupants to safety escape. S3, compartments. Definition of the separation distance. S4, exodus. Time required to reach a safe location for the occupants before the fire and the smoke creates adverse condition. The building consisted of two blocks of buildings, named respectively Block A and Block B. Block A is made of two buildings and two canopies for a total surface of 10,000 square meters, while Block B consisted of 5 buildings for a total of 6,000 square meters. In both blocks, the storage consisted of paper and cardboard reels for a total maximum height of 7.25 meters. As far as the occupants are considered, since the project refers to a working place, only occupants with a level of familiarity of the buildings in a wakefulness state are considered. The density of the occupants is of 5 people in Block A, with a training of medium level to the fire risk. As specified before, the Italian DM 3 August 2015 defines two possible solutions for 3 approaches mentioned in the previous chapter. For strategy S2, fire resistance, the standard solution given the risk level third, the solution obtained is a class 240. High cost involved due to a high level of protection of the structure and or to the presence of an active fire protection system. The FSE solution definition of a fire natural curves, analysis of the thermal time transient variation, including second order effects. For the strategy S3, compartments, separation distance with other buildings is not satisfied. Checking with the FSE solution of radiating flow and smoke temperature flow reached by nearby buildings in the five scenarios. For the strategy S4 Exodus path length longer than the ones prescribed in the regulations. FSE solution definition of performance threshold for life. S2 fire resistance. S2 fire resistance. The presence of two different types of structures, steel and concrete. Steel structures suffer of a very low thermal inertia and of a very high conduction heat transfer coefficient. For this, when analyzing the thermal transient variation, it is important to consider efforts generated by the second-order effects due to the presence of structure constraints which prevent the whole system to adjust the thermal expansion. On the other hand, the presence of concrete structure where a high thermal inertia is present with a low level of heat transport generates a high thermal gradients within the very same building elements. S3 compartments. As per the DM 3 August 2015, a threshold value of E 12.6 kilowatts per square meters is considered. The goal of FSE analysis is the evaluation of this radioactive heat transfer to nearby building and the demonstration that this threshold is not reached anywhere. S4 Exodus. For the Exodus situation, the M3 chapter of the DM 3 August 2015 defines 4 different thresholds to be verified in order to avoid the incapability of the occupant to reach a safe place independently. These 4 thresholds are visibility 10 meters at Z, 1.8 meters from ground, temperature 16 Celsius degree at Z, 1.8 meter from ground, radiations 2.5 kilowatts per square meters at Z, 1.8 meters from ground, FED and FEC 0.1. The total time the building satisfies these 4 thresholds defines the asset which needs to be compared with the asset required safe escape time. The definition of the 5 scenarios to be considered has been limited to 2. Scenario 3. This scenario has been chosen as the most dangerous given its central position with respect of the roof beam and also for the proximity of the exit 4 emergency way out. This scenario has then been used to evaluate strategy 2 and strategy 4. Scenario 4, this scenario is more risky in terms of compartments, and as it is at the center of the warehouse and it propagates quickly, reaching the peak radiating power. This is a representation of BIM model generated with Revit, which defines the FSE analysis. This is a representation of heat release rate and temperature slice of simulation. This is a representation of generalized fire distribution in the Block A building. Definition of the separation distance depending of the radiative heat transfer obtained on probes located outside of the buildings in the direction of the nearby structures. Asset verification of the four monitored parameters. Asset obtains from Pathfinder. Asset to be validated corresponds to asset obtained from Pathfinder with a margin of 100% of asset. All four monitors must be below the threshold until the asset time is reached. FSE, fire safety engineering, allowed to verify the building structure resistance for the first 15 minutes after the fire sparks. It also been possible to verify the implosive collapse to avoid damages to nearby activities. Compartments proved to be fairly distant in order to reduce radiative heat transfer. ASET and RSET analysis finally proved that the occupants can leave the building safely in the event of fire. BIM modeling has been widely used, and thanks to PyroSim and FDS, it has been possible to interact with several software and modeling in a quick and easy way, also when making engineering design iteration in the project.
Okay, I now take part in the second. I'm going to speak in the second part of the presentation. This is going to be about the scalability definition. What was good about the case just described is that it had very huge simulations to be performed, huge in terms of cell numbers, and so it was a good test case in order to evaluate the scalability. But what actually scalability means? Basically, in an FDS analysis, as long as we increase the number of hardware resources that we allocate to compute a certain simulation, we want this simulation to be completed in a lower amount of time. Okay, so if we double the hardware resources, we want to get the same results in half the time. This is the concept of scalability, and by hardware resources, what we usually mean is the CPU, which identifies the part of the hardware resource used actually for the computation, and RAM, which is the part, the memory used in the computation, the memory which is going to be used in order to allocate the mesh. It is important to notice that from an IT perspective, there are two different approaches that can be used in order to get the solutions in a shorter time. The first one is a multi-core approach in which we start from a problem, which is our FDS simulation, and this problem needs to be divided, needs to be split into sub-problems. Each of these sub-problems is going to be resolved by one single core, and then when we get the solution of the sub-problems, we're going to reconstruct everything into the final solution of the initial problem. So there is actually an operation of splitting the problem into sub-problems. And then there is a multi-thread approach, which is basically similar from before, but we're not actually splitting the problem into sub-problems. We have threads which are working together on the problem in order to get the results. FDS version 6.7.9 allows to have both these approaches, so multi-core and multi-threads, and we're going to evaluate which of the two is more efficient, in particular on the hardware, which has been taken from the Cloud HPC website, and the hardware is a second generation AMD EPYC Rome processors, which is capable of 3.1 gigahertz and has from 1 to 112 cores, and each core can be single thread or double thread. Since a multi-core approach requires our initial simulation to be divided into sub-problems, it's worthwhile remembering that we need to define multiple meshes into our FDS case and use the MPI process parameter to allocate which core is solving which mesh. In our case, we performed the simulation on 4 cores, 8 cores, and 16 cores. And we tried using the MPI process to evenly distribute the cells among the cores used for the simulations. So we got, in a 4-core case, we got about 750,000 cells per single core, which has then become 350 when using 8 cores and a little bit below 200,000 cells per single core in the 16 approach. And here you can see a graph of the mesh of the cell distributions among the several cores used into the 3 cases. In terms of results, it is quite interesting to note that in the case A, so in block A, we got a very good scalability. In here we are plotting the simulated seconds per hour of physical hour, let's say. So in case A, when doubling the number of cores, we were doubling also the speed of the simulation. This was not true for case B. That's because files were more concentrated into one single mesh, and that was slowing down a little bit the scalability part. We also got a similar scalability when we enabled multi-thread. Okay, so with threads equals to 2, yeah, we got a scalability, so performances, the simulation speed was increasing as we were increasing also the number of cores. In this case, we had just 4 cores, 8 cores, and 16 cores, so simulation speed was highly increasing. What wasn't to be noticed is that the FDS 6.7.9, the most recent version, they created a brand new solver for the multi-core approach. And this new solver was almost able to achieve the same performance in a single thread or in a multi-thread approach. So this allows us to say that the multi-core approach is very effective in the FDS 6.7.9, and it is the one recommended to be used. Instead, multi-thread approach proved to be a little bit less effective, so it can be used only when someone really needs to get results in a hurry. Scalability seems to be also quite good in the range of cells used in the current simulation, so in the range between 150,000 cells to 750 cells per each core or thread. So we recommend to use this limit and not to go way above or way below this limit, at least as far as this study has been concerned. Obviously, as side conclusions, we can say that the cloud hardware resources were quite positive because they allowed to run multiple scenarios and scalability tests at the same time simultaneously, as well as the 2nd generation AMD Epicron processor proved to be a very good solution for FDS simulation. These are the references used in order to generate the current paper and the current presentation. And we obviously thank you all for attending this presentation. In this slide, you can find the contact information both for myself, Ruggero Poletto, and also for Jordy Di Pierno in FSE PROGETTI. So we'll be very pleased if you can contact us ourselves directly using the email or telephone numbers provided here. And if you have any questions, feel free to contact us, and we'll be happy to reply to you. With this, the presentation is over. I don't know if Jordy wants to add anything to that. Yeah.
No, thanks. No.
Yeah, that's all right. So happy happy FMTC to everybody. See you later. Bye.
Bye.
Okay, great. So we did have a question here, and let me, maybe it was already answered, good. But just for the audience, regarding the paper factory, which is the reference scenario in terms of heat release rate for each of the cases you mentioned, did you consider experimental data coming from available full-scale tests? It has been demonstrated that layout of fire load, the height of storage, the free space among fire loads, et cetera, play a fundamental role in the resulting heat release rate. And I do see the experiment for tissue paper, heat release rate for tissue paper. The other issues, like layout, height of storage, free space between the fuel loads, were those considered in the work?
Yeah. Jordy, you want to reply? You want me to do it? Okay, I just carry on. So yeah, from the tissue paper, we've got the HRR curve for one single block of paper, one single reel of paper, and we allowed FDS to expand the fire to the nearby reels, okay, as the simulation, as they reach a certain level of temperature, basically. We didn't have actually access to a validation for this, okay, so we put this threshold to be quite low, considering like the data we had available, so we were more conservative in terms of the results.
Okay, let's see. Don't see any other questions in here. Are there any in the room? No questions, okay. Well, thank you very much for the presentation. We appreciate your time, and thanks for tuning in for the Q&A. It was good to see you.
Yeah, thank you, bye.